Welcome back to ECE 501B. Homework number 7 is due a week before Turkey Day. A day after Wednesday. So the next time we meet will be Wednesday. The homework is due the following day on Thursday. Your project is due at the end of the first week of December. And that material should be available on D2L for you to look at or think about and study. And I would really encourage you to quickly read the $25 billion eigenvector and see how they intersperse questions in that paper. And you can do the same thing. You can finish that paper answering the questions, or you can do something similar to a paper of your choice, or you can do something else. But that's where that is in terms of a project. What I want to do today is first remind us, maybe remind me, of where we are. And by that we will simply recap the spectral theorems and sort of show what they give us in terms of properties. Then we'll move into something new, which is positive operators. And the next topic, which I don't know if we will get to, is isometries. But when you see positive operator, think of a scaling factor. This is now an operator, not too much unlike these inner products, where the inner products gave us length or distance and angle. Now we are wanting to do similar things to these operators, which are figure out how they expand or contract, how they scale a vector. That's the positive operator property. And how they direct, or how they put an angle or a direction to a vector. And that's these isometries. Today we'll talk about these operators, and we'll talk several different ways about them. Maybe I shouldn't say definitions. I think we'll just have one definition of a positive operator. Then we'll look at some theorems associated with positive operators, some examples, and a proof. And a positive operator really has two properties. It's self-adjoint, and you can show that that operator applied to a vector when inner product with that vector is non-negative. That's the definition of a positive operator. And once we have something that's positive, we can start thinking about square roots of operators. And again, then we will look at these isometries, which, if you look at this norm behavior, S is now a operator that's an isometry. It preserves the norm. That's one of its properties. Here's a recap of where we have been. Just as a reminder, the definition of an adjoint. The adjoint is the linear operator slid from the first slot to the second slot, is one way of thinking about that. If you wanted the same inner product, but you wanted the operator to be in the second slot, then that would actually be the adjoint of the original operator T. TV inner product with W is equal to V inner product with T adjoint, or T dagger W. That's the definition of the adjoint. If you have a normal linear operator, when we say T and T dagger commute, then, or I should say, when we have a normal linear operator, that means that T and T dagger commute. Or it's norm preserving. TV's norm is the same as T dagger V's norm. Those are two ways of thinking about the same thing, which is when you have a linear operator that's normal. If you have a linear operator that's self-adjoint, that simply means that the linear operator is the same or is equal to its adjoint. And you can see what that means if you have a self-adjoint in the definition of the adjoint. Now those inner products, T just immediately, effectively, is like sliding over into the second slot. Here are our spectral theorems that we have gone over. When we have a complex inner product space V, and when the operator T is normal, it commutes with its adjoint, then a matrix representation of that linear operator can be diagonal. And a diagonal matrix is just a specialized form as a block diagonal. So we could say that it block diagonalizes a matrix, or a matrix representation is block diagonalizable when you have a normal operator in a complex inner product space. If you have a real inner product space V, and the operator is self-adjoint, which is a little more restrictive than it being normal, then the matrix representation of that linear operator can also be diagonal. And again, if I say diagonal, that's a block diagonal. It's just now the blocks are 1x1 blocks. But that's another way of describing or thinking of a diagonal matrix. If we do not get so specific on the real inner product space with our linear operator T being self-adjoint, but we say T is normal, that's not as restrictive. It just has to commute with its adjoint, the linear operator. Then the matrix representation of T can be block diagonal. And now it is truly block diagonal. We could have 1x1 blocks, or we can have 2x2 blocks along the diagonal. And the reason we have 2x2 blocks is because we might have actually underlying this a rotation or complex eigenvalues, but since we're not allowed to have those if we're dealing on a real inner product space, then we have to play with these 2x2 blocks, sub-blocks within a matrix. And that's actually theorem 725 in chapter 7. If you combine these, if you generalize a diagonal matrix to be referred to as a block diagonal in the first two, then really, as long as T is normal, then you can find a matrix representation of T that is block diagonal. If you're dealing with a complex vector space or a real vector space. So if you have a normal operator, that says now you can block diagonalize it, whether you're in a real inner product space or a complex inner product space. Now let's look at what we are going to be using now to generalize this concept of scaling with operators, which are these positive operators. Here's the definition of a positive operator. An operator T, so that really says you have a linear operator T on this inner product space V, is positive if two things are true. If T, the operator, is actually self-adjoint, which simply means that T and T dagger are the same as far as operators are concerned, and if you operate on any vector V with that linear operator T and take the inner product of TV with V, so now you have let's say the input vector V and TV representing an output vector. Now their inner product, the input with the output, you want that to be non-negative, greater than or equal to 0. And that's true for all v. And we'll start playing or looking at some particular examples of matrices that are positive. And they could then be matrix representations of certain linear operators to give us a little bit better feel for what it means to be positive, besides just really upbeat. Okay, so you miss that at home, but a positive operator, you just put on a big smile, you're always positive. Well, this is another way. So if somebody says you need to be more positive, you could say, oh, I need to be self-adjoint and I have to have a non-negative inner product relationship. So if somebody starts saying you need to be more positive, that's what you can start thinking. Self-adjoint. Oh, I need to look like my adjoint. All right, let's move on. Note, if this underlying vector space or inner product space V is complex, then the operator T is self-adjoint whenever this inner product of TV with V is real. So if you form this inner product of TV with V and it becomes real for all V, then you know that that linear operator is actually self-adjoint. Since we're good at justifying these or proving these things, let's just convince ourselves that indeed that's true. We know that one of the properties of an inner product is that it enjoys conjugate symmetry. The inner product is conjugate symmetric, which means that TVV is equal to the complex conjugate of those two slots interchanged, or the inner product with those two slots interchanged. That's one of the properties of an inner product. TV with V inner product is equal to VTV's complex conjugate, where the overbar is the complex conjugate. Now, if TV with V is real, then we know that TVV complex conjugate is equal to TVV if it's real. The number is equal to its complex conjugate if the inner product is real. So we know that fact. But if I actually look at TVV conjugate, by definition, that's the conjugate of that when I interchange the two vectors in the first and second slot. Meaning, I can interchange V and TV, but I need to take the conjugate of that. And the conjugate of the conjugate, I just get the number back. So that this is now equal to V TV. This, again, is simply using the conjugate symmetry property of the inner product. And now we have what we wanted. Therefore, TVV is equal to VTV. Since TVV up above on the right in like the second row is equal to the complex conjugate of TVV, but the complex conjugate of TVV is equal to VTV. So TVV's inner product is equal to VTV. And now we can say, therefore, and since TVV is equal to VT dagger V by definition of the adjoint, then by comparing the second slots in those last two lines tells us then that T dagger is equal to T. So it's self-adjoint. And all we required was that we needed the inner product of TVV to be real. Once we have that, then we can conclude that the operator itself is self-adjoint. So if somebody gives you TVV being real, then you can say, oh, that operator, T, is self-adjoint. Let's now mention a couple of examples of positive operators. One, we've seen one when we were doing the proof of lemma 711. The proof of 711 with T being self-adjoint and these two constants enjoying a particular relationship, alpha squared is less than 4 beta, those produce a positive operator given by T squared plus alpha T plus beta I. That linear combination of T squared plus alpha T plus beta I is a positive operator. That may be a little bit abstract. Another one is every orthogonal projection. So every orthogonal projection is positive. Before we get into looking at some matrix examples of positive operators, let's actually introduce this concept of square root in a theorem. So first, let's talk about square roots. Suppose S is a linear operator on this vector space, inner product space V. So S is the square root, that's why I'm calling it S, of a linear operator T if S squared is equal to T. So if we have S and then we operate on it again with S, that gives us S squared, and that taken together is the same as T, then we'll call S a square root of T. sort of the conventional way of thinking of a square root, or something that when you square it, you get the original back, let's say. Now let's look at a theorem before we give some examples. Theorem 727. Given a linear operator t, then the following statements are equivalent. Given t, a linear operator, the following are equivalent. The linear operator t is positive. That's the same as t being self-adjoint and all of its eigenvalues are non-negative. So if somebody says, is that operator t? And you go, I don't know, I know the eigenvalues and I know that it's self-adjoint, and if all those eigenvalues are non-negative, you can say, oh, that operator is positive, because all of these statements are equivalent. Another one that's equivalent to A or B is C, which says that t, and I'm putting in A, it doesn't mean it's necessarily the only, well, let's say t has a positive square root. T may have multiple square roots, but it has a positive square root if t is positive. T has a self-adjoint square root. And finally, E, if t is positive or any of the other statements, there exists an operator S that's a linear operator on V, such that the original operator t is equal to S dagger S. All of those statements are equivalent, and so now if you wanted to talk about an operator being positive, you could also be thinking that it satisfies all of these other statements. Or maybe it's, you've seen that one of these statements is true, now all the others are true. Let's look at some examples of these concepts dealing with matrices. Some of these might be trivially obvious, some may not be, but I would just encourage you to go home and play with them if they aren't making sense to you right now. Let's now look at square roots and positive matrices. 1. Let's say t sub 1 is 1, 0, 0, 0. A square root of that could be s sub 1. Another square root is minus 1, 0, 0. I haven't said anything about those square roots being positive or not, but both of those, when s1 hat times s1 hat will give you t1, and s1 times s1 will give you t1. 2. this one's in the book on page 145, maybe not written out as a matrix, but maybe as a linear operator. Suppose t sub 2 is now 0, 0, 1, 0, 0, 0, 0, 0, 0. A square root of that has an all 0 first column, a 1, 0, 0 second column, and a 0, 1, 0 third column. And now if you take s sub 2 and square it, you will get t sub 2. Where the first column obviously is all 0, the second column in s2 squared is just a copy of the first column, which is all 0, and the third column is just a copy of the second column, which gives us our 1, 0, 0, and t sub 2. So that one shouldn't be too hard to see. Now, knowing what we know about multiplying matrices, t sub 3. This is a really tough one. An identity matrix, what's its square root? Same thing, isn't it? What about t sub 4 being 2, 0, 0, 3? These diagonal ones are pretty easy to find square roots of. This could be plus or minus the square root of 2 and plus or minus the square root of 3 on the diagonal, and that's going to give us the square root that we want for t sub 4. T sub 5, 3 minus 4 minus 8, 11, and s sub 5 is equal to minus 1, 1, 2, minus 3. And now we can take these matrices, square roots of matrices, can have negative entries, and we can still talk about square roots. Unlike a number, then we have to introduce complex numbers if we start taking the square root of negative numbers. Here we can actually have some negative elements in our matrices and still have square roots. So there's a square root for t sub 5. T sub 6, I'm getting confused because it's the same as t sub 5, but I'm going to give a different square root. This one is now 1 minus 1 minus 2, 3. And if we look at those, if you looked at the eigenvalues of S5, you will see that those are minus 0.2679 and minus 3.732. And the eigenvalues of S sub 6 are the positive values of those previous negative numbers. So now, even when we don't necessarily have unique square roots, unless we put some more conditions on those square roots. Here I have two matrices that have just the opposite signs in terms of their eigenvalues, and they still produce the same matrix when squared. Just to keep us all honest. Let's look at now some matrices that are positive by finding these positive matrices a different way. Which Q's are positive? Suppose I say here's Q1 and it is 1, 0, 0, 2. That one you should anticipate. But here, whoops, Q1, what were the properties of a positive operator? It needed to be self-adjoint, and it had to have a particular non-negative inner product when we took the operator times a vector inner product with that same vector. That needed to be non-negative. Let's look at what that is here. Q1, is that self-adjoint? In a matrix with the standard basis or an orthonormal basis, we just need this to be equal to its complex conjugate transpose. Since it's real, we don't really have to worry about the conjugate part, but it is equal to its transpose. So Q1 is self-adjoint. Since we have Q1 is equal to Q1 transpose complex conjugate. Another way of proving that this is positive is we could use statement B in the previous theorem, where if the operator was self-adjoint and had all positive eigenvalues, then we could say, oh, that's equivalent to statement A, where statement A said that operator was positive. And here by inspection, you can see that those eigenvalues are positive. That's probably the quickest way to verify that this is a positive operator. So we could say that lambda Q1 is made up of 1 and 2, which are both non-negative, and these two taken together are statement B of theorem 727. And that then means that it's equivalent to statement A, where Q1 is now positive. But that's not really what I wanted to show. I want to actually show it from the definition of an operator being positive, which means I want to show this, and I want to show that this inner product relationship is true. I now have 1, 0, 0, 2 times some generic vector v1, v2, inner product with v1, v2, and that's the same then as the vector v1, 2, v2 when I operate on that v1, v2 with the diagonal matrix 1, 2. Now the Euclidean inner product says that I have v1 squared plus 2 v sub 2 squared, and that's non-negative for all v, let's say in R2, which now that's from the definition of a matrix or an operator being positive. We showed that it was self-adjoint, and we showed that it satisfies this inner product relationship. So Q1 is positive. Let's look at another matrix, Q sub 2. 2 minus 1 minus 1, 4. And even though it has negative elements, maybe we can still show that it's positive. Is it self-adjoint? Why is it self-adjoint? It's real, so now it just has to equal its transpose. Has to equal its complex conjugate transpose, but the conjugate doesn't do anything for us. Q2 transposed gives us Q2. So Q2 is self-adjoint. What about this inner product relationship? Now we have a little bit more going on. We have 2v1 minus v sub 2 in the first coordinate of that output vector, and we have minus v1 plus 4v sub 2 in the second coordinate of that vector q sub 2v. We have v1, v2, and now if we form the conventional inner product, we have 2v1 minus v2 times v1 plus minus v1 plus 4v2 v sub 2, or we now have 2v1 squared minus v2 v1 minus v1 v2 plus 4v sub 2 squared. Let me factor a 2 out of there since that's in all of those pieces. I now have v1 squared minus v1 v2 plus 4 v sub 2 squared. Whoops. It's the new math. 2 times 4 is equal to 4. No. That's only when you're sleepy, right? When you're tired. Now I can simply complete the square. I'm trying to show that that bracketed term is non-negative. If I did that, that wouldn't quite give me that v1, v2, but if I now have that, I now have v1 squared minus 2 times 1 half v1, v2. That's going to give me my minus v1, v2 plus a 1/4 v1, v2, and I need to take that away. Well, I'm sorry. What am I doing? Falling asleep. And I thought the new math of 2 times 4 was interesting. Is that better? So now I have what I wanted. So that now I have a plus 1/4 v sub 2 squared. I need to subtract that. Or I now have 2 times v1 minus 1 half v sub 2 squared plus 7/4 v sub 2 squared, which is non-negative. And if you couldn't show that, you could maybe find the eigenvalues of that q sub 2 and go back to theorem 727 and go, oh, I have positive eigenvalues for q sub 2. It was self-adjoint. Oh, it's positive. Another way of demonstrating the positive behavior of q sub 2. Another one. These are so fun since I'm making so many errors. I want to just see if you can catch them. So you're now my catcher. Q sub 3. Q sub 3 is 2 minus 4 minus 4, 4. Does it satisfy the first piece? Is it self-adjoint? It is equal to its transpose, and since it's real, that's all we have to worry about. Now we have q sub 3 v v. And now I can multiply that out, and I have 2v1 minus 4v sub 2 minus 4v1 plus 4v sub 2 that's now equal to 2v1 minus 4v2 v1 plus minus 4v1 plus 4v2 v sub 2 make sure I'm staying awake here. Let me factor out a 2. I have v1 squared minus 4v1 v2 plus 2v sub 2 squared. And now if I tried to complete the square, since that worked so neatly before, now I would have v1 minus 2 v sub 2 squared, and I have to add back in, or algebraically make that a addition of 0, essentially. I'm now adding 4v sub 2 squared. I need to take that away. In forming that first squared term, so that now I have 2 times the quantity v1 minus 2v sub 2 squared minus 2v sub 2 squared. And unfortunately, that's not determinate, is it? It's indeterminate. I can make this basically anything I want by the appropriate choice of v1 and v2. Where q sub 3v v, I could make that less than 0 for the choice of v equaling 1, 1. Or I could make q sub 3v v positive when v is 1, 0. So I can make that inner product have any sign I want by the choice of v. If we were to look at the eigenvalues of that original matrix q sub 3, they would be minus 1.123 and 7.123. So by any of those statements we wanted, in particular the first two, we can now say that q sub 3 is not positive. Meaning we can't just have any q sub 3 that's symmetric giving us a positive matrix. It has to be a little bit more than just symmetric if it's real. Those are some examples of matrices. Let's now see if we can start convincing ourselves of the equivalence of these statements. We've been using them or talking about them. Let's see if we can show that they are equivalent. And I'm basically going to just chase my tail. I'm going to show that A implies B, B implies C, C implies D, D implies E, and E implies A. And then I've shown that those are equivalent. So you give me any of those, I can show you that it's equivalent to the other. I may just have to chase my tail a while, but I can show you that it implies the other, whichever one you want to show. That's what I'm wanting to do. A implies B, implies C, implies D, implies E, implies A. So let's start at the first. Let's show that A implies B. And statement A, just as a reminder, said that the operator was positive. Statement A says that T is positive. And the reason why we're going through this is because actually some of these equivalences or implications are constructive, and we'll actually use some of these construction techniques later on to build up square roots, etc. So statement A says that T is positive, and a linear operator being positive says that that operator is not only self-adjoint, but it also satisfies this non-negative relationship on the inner product for all vectors V in the inner product space, capital V. That's what T being positive means by definition. If that's true for all vectors V, let's just pick a special V. And what's a special V? What vectors do we kind of like to think of as being special in this class? Eigenvectors. So now let's let V be an eigenvector. Well, if that inner product relationship is true for any V, now we've specialized it to be an eigenvector, so TV is equal to lambda V. So now we can say that lambda V is greater than or equal to 0. Since TV V is non-negative. But now we know about the homogeneity of the first slot, so that lambda can slide out of the inner product. We know that the inner product of a vector with itself, a non-negative vector, is positive, so we can divide that positive number out, and now we know that lambda is non-negative, the eigenvalues. So that says then that A implies B. And B was self-adjoint and it had positive eigenvalues, or non-negative eigenvalues. Now let's look at B implying C. Now we're given that T is self-adjoint. And remember some of these nice properties of a operator being self-adjoint. Now it has a particular basis. We can form the basis of eigenvectors where those eigenvectors are orthonormal. So now we can say that we have E1, E2 up to, let's say, E sub n form an orthonormal basis and we can say that that's true because of the spectral theorem. That's the first part of B, statement B, and the other part of B was that all the lambdas, the eigenvalues, are non-negative. If that's true, now let's go ahead and create something. Here's a let, or you could say define. And now what I want to define is actually a particular relationship. Define S. I don't know what S is yet. It's just a matrix or an operator, but it's going to operate on the jth eigenvector. And I'm going to say that that operation of SE sub j is now the square root of lambda sub j e to the j. And I'm going to say, let's do that for all of these j's. This is just a definition of S, this operator S. And I'm going to actually sort of think of S as a matrix now. If that's true, what have we just sort of created? I can now combine all these E sub j's into a matrix where it's E1, E2. These are just columns. These are eigenvectors. Let me now say that I have S, E1, E2, E sub n, and those are all equal to a scaled E1, E2, En, where they're scaled by the square root of the original eigenvalues, the positive square root of t. And to do that, I can say, oh, E1, E2, E sub n, I can scale those by the appropriate amount by putting that positive square root on the diagonal of a diagonal matrix post-multiplying those vectors, E1 through E sub n. Let me now call these, this is the same matrix. Let me just call that E. I haven't yet said anything about S, it's just some matrix. But I do know my E's and my lambdas, so I can build up all these other three pieces. And now, because I know that E1 through En is an orthonormal basis, it has an inverse. And actually, its inverse is special, but I'm just going to say inverse for now. It's an orthonormal inverse, and so you could actually say the inverse is the transpose. But let me just refer to it as the inverse, meaning let me multiply on the right, since these are matrices, by the inverse of E. If I do that, then E inverse on the left side of the equality becomes the identity, and I just end up with S, and that's equal to E. And now this diagonal matrix of positive square roots and now I've built up, since E was known, the matrix E, and these lambdas were known from the original linear operator T, I now have built my matrix S. I've now created a matrix S. It's E lambdas square rooted E inverse. If I look at that, I can also make the following. I know that S E sub j, by definition of S, was this square root of lambda sub j e to the j. If I now hit that on the left with S again, I now have S times S e to the j, which is really S squared e to the j. But that's S square root of lambda sub j e to the j. Square root of lambda sub j is a positive scalar. That can slide outside the operator, S. I now have this square root of lambda sub j, S e to the j. But S e to the j, I define that to be square root of lambda sub j e to the j, so that this is now lambda sub j e to the j. And that was t e to the j, and this is just s squared. Meaning, I now know that s squared e to the j is lambda sub j e to the j, which is t e to the j for all j. Or, I've now shown that s is actually a square root of t. Now, I need to show that it's positive. And to show that it's positive, I needed to show those two properties. So I wanted, what am I trying to show? B implies C, and C, don't look. C was I have a positive square root. I've now found that it's a square root. I now need to show that that S is positive. And to make sure that that S is positive, I need it to be, no, I need it to be a self-adjoint, and I could say all eigenvalues are non-negative, but I'm going to maybe show that it has this inner product non-negative. Okay, that's the definition of it being positive. All right, don't look. So S is a square root. Now let's see if it's positive. Is S positive? First, let's show that S is self-adjoint. Well, we know that S, we defined that to be, or we created it. Can I use this shorthand notation? Lambda to the 1/2. That's my diagonal matrix, my lambda matrix with these square roots all along the diagonal. That's E lambda to the 1/2 e to the minus 1. But I know that E inverse, because it's made up of these orthonormal eigenvectors, is equal to its transpose. Because I know of the, now what am I going to, Kronecker product nature of these E's. When you multiply those together, they're only going to be 1 when you do it with themselves, and they're 0 when they scale each other. So that's then the inverse of E is its transpose. What I'm trying to show that S is equal to its transpose. This is now S transpose, since I'm dealing with real. This is now E lambda to the 1/2 e to the minus 1 transpose. I need to reverse the order of these, so this is now E transpose transpose, reminding myself that E inverse was E transpose. Lambda to the 1/2 transpose is just lambda to the 1/2, since it's diagonal. And then I have E transpose. But E transpose transpose is E. This is lambda to the 1/2, and this is E inverse, or E transpose, and so S transpose conjugate is S, which means that it's SA. Self-adjoint. Now, we can also show that this SVV is a sum over J of A sub J squared, square root of lambda sub J. That's the absolute value of some number squared times a positive square root of lambda sub J. That's non-negative, which is what we need to show to conclude. This is the second half of our demonstration or definition that S is positive. Where did that come from? Well, let's now build any vector can be constructed by a linear combination of the basis vectors. And our basis vectors were these e's. Suppose A is now A1 E1 plus A sub 2 E sub 2 plus A sub n E sub n. SV, now those A's are scalars, they can come outside of the S, and I now have A1 S E1 plus A sub 2 S E sub 2, etc. But those S or SE sub J's were just, E sub J's were eigenvectors. We now know how those are related to the square roots of those lambdas. This is now A1 square root of lambda 1 E1 plus A sub 2 square root of lambda 2 E sub 2 and now if I wanted to look at this inner product, I now have this vector in the first slot, inner product with V, which was just a linear combination of the E's, and I know how those E's inner product, they're orthonormal, so the only ones that are going to remain are the ones with the common subscript, which means that I now have A sub 1, and I'm going to conjugate V, since that's in the second slot. I have A sub 1 times its conjugate times this scalar square root of lambda 1. So I now have the absolute value of A1 squared times the square root of lambda 1. And that just continues with all of these other pieces. I would just do this for a 2 or 3 dimensional case if you wanted to look at this, if it's not making sense now. But this now says that I have A1 times its conjugate, so that's the amplitude of A1 squared, times the square root of lambda 1, and E1 times E1 star is 1, so that goes away. I now have A sub 2 squared, square root of lambda sub 2, plus dot 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 plus A sub n, absolute value squared, square root of lambda sub n, and that's non-negative. So S is indeed self-adjoint, and it satisfies this non-negativity property of the inner product, and so S was also a square root, and now it's a positive square root. And we've built that up by construction. If we now need a positive square root, we know how to build one up. Now let's show that C implies D. Hopefully you're not looking. C was T has a positive square root, and we just found one. That was S. And D says that T has a self-adjoint square root. But what do we know about from C? C being positive already said, well, the first piece of showing that it was positive concluded that it was self-adjoint. So basically C immediately implies D. Is that clear? So we really just need to do D implies E, and that is to show that there's an operator S such that its adjoint times S gives us back the linear operator. But let's just show this C implies D. The fact that that square root in C was positive, and positive implies that by definition, that's self-adjoint, so we have D. D implies E. D is that we have a self-adjoint square root. S is now self-adjoint with S squared equal to T. That's what D says. That's the D statement, that we have a self-adjoint square root of T. So now what is T? T is equal to S squared, but S squared is just S times itself. But if S is self-adjoint, I can replace one of those S's with its adjoint, S dagger S, and that's what I needed for statement E. I needed to show that T has this factored form of S dagger S. I was able to do this because S was assumed to be self-adjoint. Now I actually need to find my tail, don't I? So I have to go from E back to A in terms of showing all of these statements are equivalent. E implies A. What was E? Well, E says that we're given T can be factored as S dagger S. That's statement E. And now let's just play with the definition or the way that the adjoint operator works. If we now look at the adjoint of T, but we express T as S dagger S, so we dagger that, and we know that the dagger operation interchanges the order of multiplication or operation. I now have S dagger, dagger, and S dagger dagger is S. So now I have that T dagger is S dagger S, which was T. So T is self-adjoint. What am I supposed to be showing? Statement A. Statement A from statement E. Statement E said that we had a factored form of T, which was S dagger S. Statement A was T is positive. So now, T being positive, we've already shown half of it, haven't we? We need it to be self-adjoint, and we need it to have this certain inner product non-negative nature. We've now shown that we've found the first piece of T being positive. Now let's find the second piece. We now can see or examine TVV's inner product. We know, though, from statement E that we can factor T, or it is factored into S dagger S V V. Now let's move the first piece of that S dagger S to the second slot. And what happens when we move an operator from the first slot to the second slot? Almost, we have to take its adjoint, don't we? That's the definition of the adjoint. So if we want to move this S dagger to the second slot from the first slot, we need to apply S dagger dagger in the second slot. Meaning we now have, this is SV inner product with S dagger dagger v. Is that okay? That's the definition of the adjoint. But S dagger dagger is just S. And by definition of the inner product, those two slots being the same says that I now have a non-negative result. Now I've shown that starting with statement E, where T is factored into an S dagger S, I've now shown that T is in fact positive, or E implies A, and now I've gone full circle, or I've actually caught my tail. Now, what we want to do is use this to show that we can actually find a unique square root for an operator. So we've proven now Theorem 727. Recall that the square root of lambda convention, or denotes, let's say, the unique non-negative square root of a non-negative number lambda. And what we want to do now is start sort of generalizing these number properties to operators. This now generalizes, and so the notation that we will use is that the square root of t, where t is some linear operator, we're going to define that to be the unique positive square root of t. So when I do the square root of an operator, that's what I'm meaning. I'm going to try to find, or that implies, the unique positive square root of that operator. And that's really what Proposition 28 actually says. It says every positive operator, which we now have a better feel, I hope, after today's material, what that means. Every positive operator on this inner product space V has a unique positive square root. And that was all, or you can recall the construction that we just performed when we were showing that statement B implied statement C. Meaning we know it's possible, and if you want to see the proof, I'm going to refer you to the textbook. And where we will pick up then on Wednesday is we will look at an example of a square root of a positive operator. We'll build one up based on that construction, where we sort of did it in general today, but let's now do it numerically. we'll find the way to, or we'll work through the way to find a square root, and then we'll get into the direction of an operator, or these isometries. We've talked about scaling with positive operators. Now we want to talk about the isometry. And we'll do that on Wednesday.